Hello and welcome to Finding All the Roots video. This is a continuation from today's class where we were finding one root, but now we're going to find as many as we possibly can, which is essentially all of them. So we have a very similar set of steps that we had in today's Go formative, which was find the degree and state the number of complex zeros, use your rational root theorem to find any possible rational roots, and then C was use synthetic division to find one root. But now we're going to find all the roots, and now our very last step is going to be write the polynomial in factored form. So we're taking that extra step, writing out from standard form to factored form. Now I'm going to be going over problems 3, 5, and 7. I don't have a blank version of these notes, so when I refer to 3, 5, and 7, I'm talking about the Go formative that we'll be working on tomorrow. So you can see I've already written up problem 3 for us. So we have f of x is equal to x to the fourth minus x cubed minus 37x squared minus 35x. And then we have x is equal to -5 here. That is a root that's already given to us. So sometimes we'll be given a root, sometimes we'll need to find all the roots, but we'll get to that in just a moment. First, let's do part A and state the degree, which in this case is 4. And the number of complex zeros, just any zeros that we're going to have. We're always going to have the same number of zeros as we have as our degree. So our number of zeros is also going to be 4. Now our very next step, part B, says to use the rational root theorem. But in order to use the rational root theorem, we have to have a constant. So what do we do with this equation when we don't have a constant? Well, with this x squared, x third, and x to the fourth, they all have an x in common. So what I'm going to do is I'm going to factor out that x so that we have x to the third minus x squared minus 37x minus 35 so that we have a constant. Now what this x by itself means is that we've already found one of our roots, or one of our zeros, at x is equal to 0. So we don't have to worry about that anymore. And now we're just going to do everything dealing with this inside section. So when we're talking about our possible roots, we're going to have p-value of 35 and a q of 1. So for part B, when we use our rational root theorem, we'll have p over q, which in this case is 35 over 1. Now I'm going to list out the factors of each of these. Factors of 35 are 1, 5, 7, and 35. The factors of 1 are just 1. When I list out all of my possible rational roots, I'm going to say x is equal to the positive and negative version of 1, 5, 7, and 35. So we have 8 different numbers we can choose from to guess and check with all these positive and negative versions. But the cool thing is, they already told us what to start with. We're going to start with a -5. So we're going to start with a -5 in our root box, and now we're going to list out all of our coefficients and use some synthetic division. Let's see, we'll bring down the first number, make sure we're adding. See, 1 times -5 is going to be -5. -1 plus -5 is a -6. -6 times -5 is a positive 30. -37 plus 30 is a -7. -7 times -5 is a, positive 35. And -35 plus 35 gives us 0. Now, this is using our factor theorem. Because we have 0 as a remainder, we know that x is equal to -5 is, in fact, going to be a factor. Now, we also knew because they told us that, but in the future, if you get a remainder of 0, that means it's a factor. Now, when we get down to 3 numbers left, meaning an x squared, in this case minus 6x minus 7, in this case, we've dealt with squareds a lot. We can factor, we can solve by undoing, we can use the quadratic formula, we can use anything we want. So in this case, I'm actually going to go through and factor this and say that this is going to be x minus 7 times x plus 1, that's going to be equal to 0. Because we're looking for two numbers that multiply to negative 7 and add to negative 6. So that's negative 7 and 1. Now, setting this equals to 0 means that I can solve for both my factors. So we'll have x minus 7 is equal to 0, and x plus 1 is equal to 0. So when I solve my left side, I get a root at x is equal to 7, and my last root when I solve is x is equal to negative 1. So if I'm going to go through and list out all of my roots for part C, I've got x is equal to 0, x is equal to negative 5, x is equal to 7, and x is equal to negative 1. But we're not done yet. Our very last step is asking us to put all of this together into our factored form. So in this case, our factored form is f of x is equal to x, or x plus 0, times x plus 5, times x minus 7, times x plus 1. And if you think about it, we already knew half of our factored form, because that's from up here in that green section. But this is our last step. So we went through, there we go. We stated our degrees and our zeros, we used our rational root theorem, we found all of our roots, and we put it in factored form. So let's try this just twice more. So problem number 5, I'm going to move this up quite a bit, there we go. That's a weird looking 5. Problem number 5 is f of x is equal to x to the 4th minus 2x cubed minus 5x squared plus 6x. So in this case, we're not given any of the roots. We just have to use our rational root theorem to help us out. So when we take a look at x to the 4th minus 2x cubed minus 5x squared plus 6x, part A is to list our degree and our number of zeros, which in this case for both will be 4. Number of zeros should be the same as degree. Then we also need to use our rational root theorem. But our rational root theorem, again, we have an x at the end. Where's our constant? Well, I'm going to factor out an x. So we have x to the 3rd minus 2x squared minus 5x plus 6, meaning that we have an x is equal to 0 as one of our roots, and there we go. And we can use what's inside here. We've got a constant. So let's see, if we do our p and our q of 1, for part B, p over q will be equal to 6 over 1. When we list out the factors of 6, we get 1, 2, 3, and 6 over the factors of 1, which is just 1. So when we list out all of our possible rational roots, we're going to say x is equal to the positive and negative version of 1, 2, 3, and 6. So again, only 8 numbers to choose from. So when we deal with part C, feel free to go around, guess and check. I always like to start with just 1 or negative 1, because sometimes that works and it's just a small number. So if I stick 1 in the box over here and I list out all of my coefficients, we get 1, negative 2, negative 5, and 6. So when I bring down the 1 times 1 gives me 1, which I'll put right here. Negative 2 plus 1 gives me negative 1. Negative 1 times 1 gives me negative 1. Negative 5 plus negative 1 gives me a negative 6. Negative 6 times 1 is a negative 6. And 6 plus negative 6 is 0. Using our factor theorem, we know this is one of our factors, so we can say that x is equal to 1. So now that I'm left with 3 numbers, an x squared, a negative x, and a negative 6, I can go through, I can use quadratic formula, I can solve by undoing. However, I'm going to factor and look for 2 numbers that multiply to negative 6 and add to negative 1. So when I do that, I get x minus 3 and x plus 2, those will be equal to 0, so that we can set each factor equal to 0, and then solve for x. So on our left side, I'm going to add 3 to both sides, and get x is equal to 3. On my right side, I'm going to subtract 2 from both sides and get x is equal to negative 2. And just like we thought, here, when we have all of our zeros of 4, or we should have 4 zeros, we have 1, 2, 3, 4 zeros. So when we list out all of our roots, we are going to have, let's see, we're going to have x is equal to 0, x is equal to 1, x is equal to negative 3, oh, pardon me, positive 3, there we go, and x is equal to negative 2. So when we list out our part D, or the whole thing in factored form, we can write that f of x is equal to x, or x plus 0, times x minus 1, times x minus 3, times x plus 2. So let's try just one more problem, and let's make it a little bit more interesting. What if, in this case, we didn't have any, what if they weren't all rational roots? What if they were irrational or imaginary? What would we do? Well, let's try one more problem. This will be problem number 7 from the Go-formative. This is f of x is equal to x to the 4th minus 81. Short and sweet. So again, for our degree and our number of zeros, they're both going to be 4. We'll look at the highest exponent. And then for our rational root theorem, our p and our q, that's the only thing we have listed. So our p over q is going to be 81 over 1. And when we list all the factors of 81, that'll be 1, 3, 9, 27, and 81 over all the factors of 1, which is just 1. So we'll have, that x is equal to the positive and negative version of 1, 3, 9, 27, and 81. So here we'll start guessing and checking. Sometimes you may not get it on the first try. That's okay. For the sake of this video, I'm going to start with a 3, just because I know how that's going to turn out. But remember, when you're doing your synthetic division, put a placeholder. So we have a 1 for the x fourth, and then we'll have placeholders for a 0, x cubed, 0, x squared, 0x, and then a negative 81. If you don't have those zeros there, it's going to mess you up. But we'll continue our synthetic division as we have been doing. So 1 times 3 gives me 3. 0 plus 3 is 3. 3 times 3 is 9. 0 plus 9 is 9. 9 times 3 is 27. 0 plus 27 is 27. 27 times 3 is 81. And negative 81 plus 81 is 0. So because our remainder is 0, we know we've done this correctly. And we have a root at x is equal to 3. Now, right here what we have left is x to the 3rd plus 3x squared plus 9x plus 27. I'm not down to an x squared yet, so I'm going to keep going. So I can go back up here to find any of these roots. With teacher knowledge, I'm going to start with a negative 3. So if we use negative 3, now we're not going to do it with our original factors, coefficients, original coefficients. We're going to do it with our new coefficients here, so it's a little bit shorter. So we'll use 1, 3, 9, and 27. Bring down the 1. 1 times negative 3 is negative 3. 3 plus negative 3 is 0. 0 times negative 3 is negative 3. Oh, pardon me. No, it's not. It's 0. Excuse me. It's been a long day. 9 plus 0 is 9. 9 times negative 3 is a negative 27. And 27 plus a negative 27 gives us 0, which means we have found a root when x is equal to negative 3. So when we rewrite this equation, we get x squared plus 9, since we have a 0 for our x. Now normally I'd look at this and go, oh, it's a difference of squares, but you know what? It's not, because we have that plus there. So this isn't something we can factor. So instead of factoring this, I'm going to take this equation set this equal to 0, and try and solve. You can also use the quadratic formula if you want. But from here, I'm going to subtract 9 on both sides. So I get x squared is equal to negative 9. And to get x by itself, I'm going to square root both sides. Whoops. So we get x is equal to the positive and negative version of the square root of negative 9. Now, if I think back to a couple units ago, I go, you know what? When I have a negative under the square root, that becomes an I outside of the square root. So we have x equal to the positive and negative version of I times the square root of 9. But we know what the square root of 9 is. That's going to be 3. So this is really x is equal to the positive and the negative version of 3i. So in this case, we have some imaginary roots. If you get down to your squareds and you can't factor, try your quadratic formula, this is solving by undoing, and see what you can get. But we can see that with our roots, we do have 4 roots, just like we predicted. We have x is equal to 3, x is equal to negative 3, x is equal to 3i, and x is equal to negative 3i. Now, when I go through and I list my factored form, we don't like having imaginary roots because that's not something we can really deal with. So I'm going to write it like this in my factored form. So when we do part D, I'm going to move this up just a little bit more, we'll have f of x is equal to x minus 3 times x plus 3. And then instead of dealing with 3i and negative 3i separately, we're going to deal with them as one, not as individual imaginary roots, but just as x squared plus 9. So whatever the thing is that you factored or solved with, that's what we're going to leave in there. And this is our final answer. So we'll practice some more of these tomorrow of finding all of the roots. This is the last of the brand new material. So let me know if you have any questions, and I look forward to seeing you tomorrow.